let's start reviewing what the goal is and what we covered last time, and then we will go in a different direction today because it will be mainly a review. We have to follow some argument in harmonic analysis that we will need to justify some step. But one thing that our goal was to understand the Hardy uncertainty principle. This say if F and the Fourier transform are in L2, then if A multiplied by B is larger than or equal to 1, then F is 0. Then we translate this uncertainty principle to the linear Schrodinger equation. How? Then we saw, we're going to translate this to solution of the free Schrodinger equation. If we call this the free Schrodinger equation, that's completely constant coefficient as before, we saw that the solution is given by this formula or by this one and the last one can be written this way. Maybe with a strong sign. Therefore, if we pass this to this side and we take absolute value, then you can say that the solution in absolute value at the time t is just the Fourier transform of this quantity evaluated at this point. This doesn't change the L2 nor, then we can, if we rephrase this principle in this form, therefore Hardy say the following. If U0 and and this is sharp. If you take the appropriate Gaussian solution, you will see that you have that this is resolution. It's sharp. Okay? That tells you that Okay, then what the goal is, the proof of this is just to rephrase that. Okay? Then what we want is to use this to extend this kind of result to non-constant coefficient. Extend this to non-constant coefficient and see what can we say to solution of nonlinear Schrodinger equation. Okay? And of course, we have chosen the Hardy version in L2 because this solution of this is a group in L2. Then if you start in L2, you stay in L2. This is not true in LP. But you can ask another associative principle, like if you start with compact support, can you prove that you don't have exponential decay later on and so forth? There are other questions. And as we say, if we want to extend this result to solution of Schrodinger equation with potential, then we have out, we don't have this formula anymore. We are not, the formula is not of this source. Therefore, you say, how can I prove something like this? Well, ask yourself a simple question. How can you prove this result without using analyticity? Because the proof of this is based on this, and anything that uses a certainty principle of this source, as we saw Hormander, use this. By the way, Hormander proof, what we prove by Hormander give a proof of this, the same. In one dimension, but therefore, the first thing that we need is to be able to obtain a result of this source without using analyticity. For any t. For any t, this is true. Any t. If on any t you have this decay, if I do the right computation, if the numbers are correct, if you have this for any t, if there exists t, this thing. In particular, for example, let's keep, then our first goal will not be to extend it to potential or to nonlinear, but to be able to give a proof that this doesn't rely on analytic function techniques. For example, let's take the following case. And let's put this number in to use that on Monday. If t is equal to 1 and a is equal to b, the condition is that a is larger than 1 over pi. Okay? On Monday, we are going to give a very simple argument that doesn't reach this, but is not based in analytic technique. This would be formal Kleinerman estimate, but it will give you the proof without analyticity, but you don't reach exactly this value. To justify this formal argument that we will give on Monday, we need to use a lot of harmonic analysis, and that's what we are going to spend today's class. Okay? Any question with this that we will postpone until Monday? Okay. Then, and we will do a review of the Hilbert transform that we already started last time. And the motivation was this one. Suppose that you have f from R to R real, and you want to solve this problem. by taking Fourier transform in the x variable, right? You can solve, you are looking for an harmonic extension of some function that you have prescribed here. And that was given by convolution with this kernel. We did all the computation. In the x variable. I mean that this is 1 over pi x minus t. Okay. Then the kernel in this case, that is Poisson, is where p of x is 1 over pi 1 over 1 plus x squared. And this is a very nice kernel. It's positive, decreasing, L1, and so forth. Okay? And this is exactly 1 over pi, the real part of I over C. Let's see that this is correct. If you put I over C is equal to x squared plus y squared. Okay. Then, well, this one not. We have to put the y there. The real part of this is exactly this kernel that we have here. Okay? Therefore, if we want to find a harmonic extension of this function f, we take convolution with this kernel in the x variable. Y is the parameter that tells you which is the high. Then you have here, you start with f, you go to u, and then you try, u is harmonic, and we try to find a harmonic conjugate here, b. Of course, if we want to find an harmonic conjugate, we take convolution with the imaginary part of this. Then b is going to be convolution with the imaginary part of this one. But the imaginary part of that is x over this, right? Then it's going to be no. Okay. You have to correct me, please. I mean, otherwise, okay. The imaginary part is have the x in the top. Is this one? Okay. This is the harmonic conjugate of this. That means that you are taking kernel, your kernel is this one, where q of x is x 1 over pi 1 plus 1 squared. And this is not positive, it's not in L1, and it has no property that you would like to. I mean, the only good thing is that it's odd. Okay. Then you ask the question, what is the boundary value that you reach when you take the limit here? What is the limit when y tends to 0 of q y convolution with f of x? Then since this is important, you will see that you can prove that this is going to be equal to 1 convolution with the principal value of 1 over x of f of x. Then when you take limit in this kernel, I have the y here. You're going to converge to this formally, but you have to preserve the property that this one is odd. then you will see that what you have is the principal value. What do you mean for this? This is going to be 1 over pi, the limit It's not too complicated to prove this. You just have to say that you have this for x between y and this, and take the difference of these two and prove that this goes to 0. Okay? Therefore, this is what is called the Hilbert transform. Then you start with any function, you take the harmonic extension, you take the harmonic conjugate, and you take the boundary value of that, you recover the Hilbert transform. And the Hilbert transform, if you want to go straight from here to here, is the convolution with the principal value of 1 over x with 1 over pi, when the principal value means this limit. Okay? Okay, it's not clear why this is going to make sense. Okay, let's define this for the moment. The Hilbert transform of f of x is 1 over pi, the limit when epsilon tends to 0. I have to correct it, of this quantity. Okay, suppose that you say, why this integral make any sense? Right? For example, in 0, why this is going to make sense? What do you need for this to make sense? You're trying to say the Hilbert transform in 0, what is this make sense? Well, you want to see if this limit exists, and now you use that this quantity is equal to this. For example, if you want to make sense of this, you write this quantity here. You are using that this is a constant. The integral of 1 over t, since this is odd and this interval is symmetric, is 0. Here you are multiplying and divided by t. You are not doing anything. Now, if your function is differentiable, this is bounded by a multiple of t, and then this integral makes sense when you take the limit, and this makes sense. Then this makes perfectly sense if the derivatives of f is inner infinity, and t and x multiplied by f is inner infinity, for example. You bound this makes sense. Then this is by the mean value theorem is bounded by the derivatives, and then you kill the singularity at 0. Then if this makes sense, then this makes perfectly sense. Okay? But we need more properties of this. Let's see that if we can define this in terms of the Fourier transform. For this, we want to define the Fourier transform of principal value of 1 over x. Okay, now we have to be careful. What do you mean Fourier transform of this? This is not an L1, you're taking some limit and so forth. Well, this is a distribution. And if you want to take Fourier transform, you have to say that this is a temporal distribution, right? Then this makes sense when you apply this to a nice function. In the Schwartz class, these are the functions that decay very fast and so forth. We defined that in the first. Okay, then this is defined this way. And this temporal distribution applied to a Schwartz function is defined as the action of this over this in an integral. Therefore, this is the limit. This is the integral between minus infinity and infinity of E prime of X. Is this okay? This is the action of this. Okay. Now, then you say this is exactly equal to you write what is this? This is okay. Okay, now for every epsilon, this function is integrable, this function is extremely nice, then you can apply Fubini as far as you don't pass the limit inside yet. Then this is exactly the integral between minus infinity and infinity. Then you have phi of y here, and you're going to have the integral here between x. Then you have exponential of 2 pi I x y x dx, and then dy. Then you are integrated in a symmetric interval. These have a cosine part and sine part. The cosine is even, then with the x, give you odd, cancel. Therefore, this integral is just this. Minus I sine 2 pi x y over x dx. Right? And now you remember that the integral between minus infinity and infinity of the sine of t over t is 2 pi. No, it's just pi. You change variable, and when you do all this, you're going to, when you take now the limit inside, this is independent of the epsilon in here, you take this limit of, and you're going to have that this is exactly the sine minus I, the sine of y multiplied by pi here, but you have another pi here. Therefore, this is give you the integral between minus infinity and infinity phi of y minus I sine of y dy. I think this is correct. Okay, did you compute this? You have a minus there. Is this okay? Therefore, the Fourier transform of this, all this quantity is equal to this value. because this is the action over this nice function. Then you have proof that okay. We need this graph, but we don't need this formula anymore. Therefore, we can go here. The Hilbert transform is this, that is exactly 1 over pi, the principal value of 1 over x, convolution with f. Then if you take Fourier transform forward and backward, this is then you start with f here, and you are taking convolution with 1 over pi principal value of 1 over x, convolution with f. If you take Fourier transform here, and you multiply by this, Fourier transform of this one, this is Fourier transform, this is Fourier transform inverse, this is one. If instead of taking convolution from here to here, you take Fourier transform, you multiply by the Fourier transform of this, that is minus I sine of phi, and you go back, you are doing exactly the same business, because if you take Fourier transform and Fourier inverse, you are not doing anything. Fourier transform of this of the convolution is the product of Fourier transform. Therefore, to go directly is exactly to go like this. Therefore, this is exactly equal to minus I sine of c f of c backward Fourier transform. Then we can define the Hilbert transform in this way or that way. Any question? Okay. Okay. And we need the Hilbert transform because okay, let me finish with the Hilbert transform and justify where are we going to use that. Then, with this definition, you take a function in L2, you take the Fourier transform, and you still are in L2, you preserve that. If you multiply by this quantity that have absolute value 1, you don't change, and you take Fourier transform that. No operation change, then the Hilbert transform is a unitary operator from L2 to L2. Then we would like to see what is the action in other LP spaces. Okay. Then how are we going to do that? Okay. Before we go there, let me see. Suppose that you have the following operator, the projection into the positive frequency. You take a function f, you take the Fourier transform, you take the multiply by the positive value here, and you get this. Okay? You take a function, you take his Fourier transform, you multiply only by the positive, you kill all the negative frequency, and you go back. Okay, what is the relation between positive projection and the Hilbert transform? Well, you are multiplying, in the side of the Fourier transform, you are multiplying by this. If you take I, the Hilbert transform, is exactly multiplication in this part by the sign. Then it's multiplication by this. The symbol of this operator means symbol is what you multiply Fourier transform before you're going backward. Then the symbol of this is the sign. Okay, how you pass from here to here? Well, you add 1 and divide it by 2, right? Therefore, you say, if I add the identity plus I this, then I adding 1 and I divide it by 2, I get the positive projection. Then if you want, for example, the projection to preserve the L2, then you have it because this preserves the L2, this one is continuous in L2, then this is continuous in L2. Then you don't preserve the quantity, but you are continuous in L2. Then everything that you need to know about projection operators, you have to refer to the Hilbert transform. Okay? Then we are going to use that in this way. Okay. Then let's try to understand one more thing about the Hilbert transform. What is exactly the derivative? If you do this graph, suppose that f is a function of one variable, you take derivative, that is an unbounded operator. You take, what is exactly this? What do you have? You go Fourier transform, Fourier inverse. Then to take derivatives, we saw that this is exactly equal to multiply by 2 pi ci f c, right? Is that with the right sign? Is that plus the right sign? Or? Therefore, if I take Fourier transform inverse, I have this. Therefore, to take derivatives is exactly to take the Fourier transform to multiply here by 2 pi I c and go back. Then to take derivatives is just multiply by this polynomial that happens to be an homogeneous function of order 1. If you want to multiply by k here, you take k here, and you take k and k, k. Then, when you take the derivatives of order k, you have a homogeneous polynomial of order k. Since you are in one dimension, you only have one possibility. Okay, then what is exactly the Hilbert transform? The Hilbert transform is doing this. Is taking the Fourier transform multiplied by the I sign and going backwards. Then the symbol that you put here is this one. This one happened to be bounded. Therefore, this is a bounded operator. Since this is in L2, this is a unitary operator, and this is a unitary operator, this is unbounded, then this operation is unbounded. Here you are bounded. But more important, if you take derivatives of order k, you have an homogeneous polynomial of order k. Here you have an homogeneous polynomial of order 0. The sign is the only homogeneous function except for a multiple of order 0, right? Then you think that the Hilbert transform is an operator of order 0. It's a derivative of order 0. Okay? Is that a good motivation? I mean, this is an homogeneous of order 0. When this is an homogeneous of order k, homogeneous, a function is homogeneous, phi homogeneous of order k if phi lambda. Then if you evaluate the sign in here, you have power 0 here, doesn't matter. If you, here this is homogeneous of order k, because, okay, now let's discover that we have an extra operation with the Hilbert transform. What happened, since this is what we have. With this graph, you start with U, you have the harmonic extension of U called UF, you have the harmonic conjugate, and you take, this is the limit, and this function f, that depends on, is UF plus IBF, is analytic in the upper half plane. Suppose that you start with G. Do the same operation with G. Start with G, you extend it in harmonic. You take the conjugate, and you go backward here. You take this is Hilbert transform of G. Okay. Then you do this. You have U of G. Okay. Then the product of these two functions is analytic. And what is the product of these two functions? Well, the real with the real, the imaginary with the imaginary with a minus, plus I, and now you have UF BG plus U BF UG. Okay? This is an analytic in the upper half plane. What does this tell you? That whenever you have this, the boundary part of the real part give you the boundary value of the imaginary part. Then you take the boundary value of the real part, you compute the Hilbert transform, and you have the boundary value. Then do that here, which is then the Hilbert transform of this one, the Hilbert transform of what you put in the real part give you the imaginary part. Then the Hilbert transform of this boundary value is exactly this boundary value. Because this is what you discover. You take this is going to be the real part, and the imaginary part will be the Hilbert transform. This is the real part. The imaginary part is the Hilbert transform. Then what is the boundary value of this? Well, the boundary value of this is F. The boundary value of U, G is G. The boundary value of B of F is H of F. The boundary value of B of G is this. And this is exactly the boundary value of this, that is F H of G plus G H of F. Then you discover that you have this formula. Hilbert transform of Fg is equal to F Hilbert transform of G plus G Hilbert transform of F plus Hilbert transform of the Hilbert transform of this. That is U1 is a very tricky formula. It's like a Leibniz rule for derivatives of order 0 that doesn't hold anywhere except the Hilbert transform. I mean, if you have something like this in higher dimension, it will be extremely nice, but it's not true. I mean, the generalization of Hilbert transform in higher dimension is something called Ries operator, and you have nothing like this. This is pointwise, completely pointwise. Okay? Okay, you have this nice formula. we want to prove that the Hilbert transform map LP into LP continuously. Demand that there is, for all P in 1 infinity, there exists CP such that H Hilbert of P CP of this. And this constant CP goes to infinity as P goes to 1 or P goes to infinity in a very precise way, but we don't get into that. Okay? Let's try to prove this. Okay, the way that you prove this is proving that the Hilbert transform doesn't send L1 into L1 and send L1 into something L1 weak, but we want to avoid all technicalities at this point. We will not be able to avoid that in the next step, that is the maximal function. Let's use this formula to prove this. Okay, then we need a general theorem that says the following. Theorem, Ries-Thorne interpolation theorem. Suppose that you have X, B and mu is a mesh. I mean, this is a set. This is a sigma algebra. This is a measure. Suppose that you have an operator T. Suppose that P0 is different than P1, and Q0 are different than Q1, and Qj and Pj are between 1 and infinity. If T go from LP0 into this space, I'm going to write this. And for all f in LP0 of x, T of f in LQ0 is less than this constant. And suppose that T is continuous or is bounded, it means exactly this. Suppose that you are continuous from P0 to Q0, from P1 to Q1, and this is the constant that gives you the boundedness, and this is the constant that gives you the boundedness. Then, for all theta between 0 and 1, we have if let 1 over p theta be 1 minus theta p1 theta p 0 p1. 1 over q theta is equal to 1 minus theta q0 theta q1. Then T send LP0, LP theta into LQ theta continuously. That exists. Okay, I don't have to write what is this node, right? LQ. Is that clear? And you have, moreover, this constant is less than this one. Okay, what this is telling you, if you are, typical graph is this. This is 1 over p. Since p is more than 1, you go up to 1. If p, this is 1 over q. What you are saying is you are not in the same, you don't start in the same level. Yeah. Then this is 1 over p, 0, 1 over q, 0. And this is 1 over p1, 1 over q1. This combination is give you, if you have continuity here, you get continuity in the middle. That's what you're saying. And moreover, the constant is bounded by a logarithmic combination of these two. Okay, this theorem is a consequence of the three-line theorem in complex variable. We will not do it, but this is something that we are going to accept. Okay? And most of the time, this is Rn, this is the Vex, and this is the Vex measure. Okay, let's see how we can use this rule to prove that. Let's use this trick. Okay, let's try to use this trick to prove that we have continuity outside L2. Okay, let's suppose that we take in this formula, to prove the claim, take G equal to F. Okay? Therefore, you have that the Hilbert transform of F squared minus twice F Hilbert transform of F is equal to the Hilbert transform of the Hilbert transform of F squared. Okay, I pass, this is, you pass to the other side and you have this. Now take the L2 node. F Okay, this is the Hilbert transform of, by triangular inequality is this. Okay, now you use that the Hilbert transform preserve the L2 node. Therefore, this is equal to the Hilbert transform square 2. But if you take the square of a function, you compute the L2 node, you are computing the L4 node to the power 2. Right? L4. Thank you. Therefore, this, since you preserve the L2 node here, this is equal F squared L2 plus 2. Now I use holder. Then this is L4 here, L4 here. And now this is lesser or equal. In fact, it's equal, but let's put a lesser or equal, it doesn't matter. This is Hilbert transform, this is the L4 node square, right? And now I can use Young inequality and do this. this is, I put this one, let's maybe, A multiplied by B is, let's do this is 4 F L4 squared plus 1/2 Hilbert transform of F squared 2. You use that A, 2 times AB is less, I put the square root of 2 here, the square root of 2 here. This is 2A B over 2, right? Or maybe I can put 2 here. Okay. Now, this is what you want, this is what you get. Since you have 1/2 here, you can pass that by paying by 2, and you add this, you get the L4. You pass this side here, then you have that the Hilbert transform in L4 squared is less than, you have a 2 there, you have 1/2, you pass 2 here, then you have maybe 6. Of course, this is not going to be anything sharp. Then you prove L4 continuity. And now that you have L2 and L4, you go here and you have everything between 2 and 4. Okay? Then, if you reapply this with 8 now, because you know that in 4, you keep going and get all the powers that are more than 2. If you use a join, you pass to the P that are less than 2. You use the adjoint of the Hilbert transform, is practically the same one. Okay. In all this, I have done everything. I haven't justified one step. And this is a step if when you are in unique continuation. Not here. Here is okay. But if you are in unique continuation, this is the step that you cannot miss, because then you can prove things that are false. What is the step that I'm doing that I haven't justified? I mean, if you accept the step that I did this, we can prove a lot of things, right? But maybe we can prove things that are false. I pass this to the other side, and I subtract another thing. I'm assuming that this is finite. When I pass this to the other side, I'm assuming that this is finite. It's finite. You can justify that in this step. But when you're working, you need continuation. You have to be sure that everything that you pass something to the other side is finite, because otherwise you have plenty of examples that you can prove things that are false. You are using this. Here I pass this to that side. Okay, there's no problem to justify that this is finite. Start with the Schwarz class and justify that. Okay? Then we have proved this. Is this okay? Okay, you will see that this is one of the, to justify the manipulation of things in unique continuation. It's not a problem there. Okay. Then we need one more thing that is extremely important for the Hilbert transform. Okay, the Hilbert transform is, roughly speaking, a derivative of order 0, because the symbol is homogeneous of order 0. It has something that is like a Leibniz rule, but it's not a Leibniz rule, but it's like a Leibniz rule. It's a very nice, the derivatives of the product, the derivatives of the verb by the second, and so forth. Okay, there is something that is very important. Theorem. Calderon commutator theorem. It says the following: if you take you commute the Hilbert transform with a multiplication by A in LP, this is less than some constant that depends on P, the derivatives of A in L infinity, F in P. Okay. Okay, let's try to understand this. If you have a differential operator, derivatives of order K, And you commute this with a multiplication by A and apply to F. What do you have? You have the derivatives of the product minus, you're commuting these two operators, A derivatives of order K of F. As an operator in F, what is the largest derivatives that appear? You kill the derivatives of order. When you take the Leibniz rule here, the derivatives, when this derivative hit here, is exactly this term. All the derivatives that is this is an operator of order K minus 1 in F. Right? When you commute to differential operators, you lose 1 degree. This is a multiplication by A is an operator of order 0. Differentiation of order K is an operator of order K. You commute, you have order K minus 1. Well, roughly speaking, this is the same. This is an operator of order 0 because it's a Hilbert transform. That is the symbol have derivatives of order 0. This is multiplication by A. That is an order 0. Then this should be an operator of order minus 1. Therefore, when you compose with this that is have order 1, you still have order 0. Okay, that this is a very important estimate. Okay. We will expand this, but we will leave it up to now like this. Okay, let's see that. For example, try to compute this explicitly. You can compute. This is you see that this formula is much nicer when, for example, in this case, that is a Hilbert transform of this minus compute that. I mean, you only need that the derivatives of this is going to be A have to be bounded. You see that in this case, you have 0. They really commute. Okay, we need, this is something that we will use when we are going to justify the step in the next, some of the steps that we will do in the next class. Okay. Unfortunately, we need another operator that is not the Hilbert transform. And this will be the last one that we introduce, but we have to introduce this one. And this is the one that controls all the business. Okay, we have to define the following. Okay, we're going to define the Hardy-Littlewood mark. Maximal function. Okay, what is we call you take F to simplify your life to suppose that this is an L1 log. Make it integrable to simplify it now. You take the ball of center X and radius R, and you take the average of your function over this ball. And you take this over all possible balls. And you call that the maximal function of F evaluated at X. Now let's try to understand what you're really doing here. This is supremum over 1 over the ball of center 0 and radius r, the characteristic of the function that is this convolution with absolute value of f in x. If you write this, you get exactly this. Right? Because when you evaluate this, then you are taking, well, this is the measure of that. Okay. Then you are taking convolution with all the possible radius. You can be very thin or like this. If you are in one with all the possibility that you have, this is total mass is 1. Okay? And this is an average because you are integrating. If you take the function 1, you get 1 everywhere. Okay. This is an operator, but they have two problems. First, it's nonlinear. Why is nonlinear? Well, first, you put absolute value that kills the linearity, and second, you're taking supremum. It's nonlinear, right? Both of them. Then it's sublinear. Notice that n of f plus g of x, point-wise, is m of f x n of g of x. Sublinear, semi-linear or something like that. Okay. Sometimes you want to do this in balls. Sometimes you want to do this in cube. And you want to avoid rectangle because then if you do it with rectangles, things start to be weird when the rectangles can be very thin. Okay? But you sometimes want to go with cubes, sometimes you want to go with balls. Sometimes you want the center of the ball to be x, and sometimes you only care that the ball contain x. Then let's put this one, m star of f of x is equal to the supremum over all possible balls such that x belongs there. And then you take you are taking now all the possible balls. You don't have to be the center. You just need to contain this point. Certainly, this is more than that, because you are taking supremum in a bigger set. But that one is bigger than this one if you multiply by a constant that depends on the dimension. Right? Because suppose that you take this ball and you are here. Okay? Then this is the radius of this ball. You take now then you have this m of f n f of x is less than n star of f of x, and is less than some constant that depends on the dimension n of f of x. Okay. If you do, okay, you are taking this radius. Suppose, I mean, this is one double view, this is the radius, this is your x. Okay? Then what you have here, now you take the radius 2r, and now you are in the center of that. Okay? Now you are in this one of these guys, and you're going to say, well, but you are not integrated. There is a factor to pass from here to here. There is a factor 2 to the n. Then I don't know. This might be 2 to the n. Okay. The same business if you take cube. Okay. If you take the maximal of a cube, maximal of a cube. This is saying you can take the cube, the center, you're going to put that this is a cube and the center of the cube is x, or you cannot put it on the center, it will be the same. Okay. Okay. Then we don't have any hope to let's do an example to see that we would like this maximal function to send function from L1 to L1, and let's see that this is not the case. Okay, let's see an example. Suppose that we are in one dimension. Suppose that we take f, the characteristic function of minus 1, 1, means that we are here. This is our function. Okay, suppose that we take x very large here. And we take the radius equal to the absolute value of x. That means that we are going to integrate in the ball of center x and radius r. We are going to integrate up to 2x. Then we take the ball of center x and radius absolute value of x. And if we integrate that, we have our f that is positive. We don't have to add this. We are taking this part that is 1. Then this integral is 1. And what is the measure of the ball of center x and radius absolute value of x is 2x. Therefore, you have that the maximal function of the characteristic of minus 1, 1 of x is larger than this. Because, I mean, you're going to take supremum, and when one of them you reach this. This function is not in L1, even that this one is in L1. Therefore, you are missing the L1. Okay? Then this is not in L1. However, we have that you send L infinity to L infinity, right? If this function is bounded by 20, doesn't matter if the average anywhere will be bounded by 20. Therefore, we have this, the maximal function of f. Doesn't matter if you put it in the center or not, because it's up to constant. But let's put it in the center to make it nicer. It's bounded by this. Then we miss the L1. You came out that, okay, you are not in L1, but you are almost in L1. This function, 1 over x, absolute value of x, is not in L1, but it's in L1 weak. Okay, what? Okay. Then you don't, what you have is this. Okay, I erase that. You would like to have this. And we don't have it. Okay, the maximal function. But we have this. You take the set where you are larger than lambda. And you measure this set, and you multiply by lambda. This is less than the L1 norm of G. Right? Let's prove this is Chebyshev inequality in L1, right? For all lambda positive. Okay, why this is true is you have this set. If you integrate over the set where g of x is more than lambda, this is exactly the measure of this set. Since you are integrating 1 and you are integrating just when g is like this is less if I integrate a bigger function, g of x over lambda, over this set. And this is less if I integrate in the whole domain. Therefore, if I pass lambda to the other side, I have this. Then this is always true. The supremum over lambda of the measure of lambda multiplied by the measure the maximal function of f of x is larger than lambda. I don't have to put absolute value because it's always positive. Okay? Then this is always true because this is Chebyshev. This is false. We just saw it. But what is true is this. The L1 of this doesn't bound this quantity, but is bound this quantity that is a little bit smaller. Okay? And this is good enough because we have something called Marcinkiewicz theorem that say if you bound this kind of sense that is like defined that if this is finite, this is like to be L1 weak. Okay, then not try to go into L1 weak and all these things. But if you miss to be continuous, but you can bound this part, you can still interpolate. You have to be below the diagonal to be true. But since we are in the diagonal, 1, 1, and infinity, we have the result. Let's write the Marcinkiewicz theorem, and then let's say. Okay. Marcinkiewicz theorem says exactly the same thing. And Marcinkiewicz theorem, suppose that T, okay, let's state it in the what we needed. Suppose that we have a T that goes from L1 in x plus L infinity of x into nice function. Suppose T is sublinear. Sublinear is this. Suppose that you are that, let's do it exactly like this. Suppose that the supremum in lambda positive of lambda multiplied by the measure. Okay, then if I put this, I have to put mu. The maximal function of f, well, I have to put t, because I'm trying to do it in general, t of f of x lambda is less than some constant L1. Suppose that Tf of L infinity is less than L infinity with another constant. That implies you don't have continuity in this extremal, but you have continuity that for all p, between 1 and infinity, you have continuity. T of f, p is less than some constant p, f. And you're going to say, why do you need the previous theorem if you have this one, right? The previous theorem asks for being linear. As for this one, not this one, as for the L1 here. The previous theorem needs this. You are putting less than that. Right? Why do you want to have this theorem? What is the advantage of this theorem? Well, the advantage is that you don't have to be linear. Second advantage is that you don't have to be continuous in the extremal. You can have the two extremal to be kind of weak of that. And to have a strong continuity in between. What is the disadvantage? That you have to be in the diagonal or below the diagonal. And second disadvantage is that this node, the control of this node is very bad. You don't have good control of this node. And the other one, this node was bounded by a convex combination of logarithmic convex combination of this one with this one. Okay? Therefore, if you have this, you have this result. Then we have that the maximal function of f in LP is less than some constant p f in LP for all p between 1 and infinity, where the maximal function of f of x is the supremum Okay. Okay, let's prove two things with the maximal function. We're going to prove two things. The hard-deletable Sobolev, that is the sharp Sobolev estimate, that all the other ones will be. Okay? And second, we are going to ask the question about the continuity of the maximal function with weight. But let's go first to the hard-deletable Sobolev estimate. And that is and since these are the last two things, let's go slow because we are going to have more than two indexes, and that's kind of hard to do it when you are very close to the board. It's easier when you are far from the board, when you have to manipulate two indexes. Well, the hard-deletable Sobolev is this. Okay, what is a hard-deletable Sobolev say? Suppose that you have a number alpha between 0 and the dimension. Suppose that you have p is less than q, less than infinity u. No 1 is equal to 1 over infinity. Suppose that you have this rule, 1 over q is 1 over p minus alpha over n. And suppose that you take this convolution, I sub alpha of f, as a function of x is some constant that depends on alpha and n, convolution n minus alpha with f. Then you have this estimate. E sub alpha f in LQ is less than some constant f in LP. Okay. Let's see what you're saying. In general, when you take convolution, roughly speaking, when you convolve two things, you get something better. Right? That is not very serious what I'm saying. You are convolved this function that is in LP, that P is below Q, and when you convolve, you get into LQ that is a little bit better. How better is it given by this rule? Okay? then you are improving by taking convolution with this kernel. You are taking convolution with this kernel. How good is this kernel? Well, that kernel is not good at all because it's not in L1 at infinity. Okay? Okay. Okay, but let's try to see what. But that you are really saying is that you are taking derivatives in some sense. Okay. Let's review that. And you will see that we need the maximal function to prove that. Okay, let's try to rephrase that. What is the derivative with respect to x of j of f of x? It's exactly if you take Fourier transform and you go back. But taking Fourier transform is 2 pi I c sub j f of x. Okay? Therefore, if you take the Laplacian of f, is, or minus Laplacian, is the sum of x1, x1, x squared, xn, xn, squared of f. That if you go here, then you're going to have 4 pi squared c squared because f. Then to take the Laplacian is to multiply, then to take the Laplacian, or minus Laplacian, is just to take Fourier transform, multiply by 4 pi squared c, and go back with the Fourier transform. Okay, you take Fourier transform here, you multiply by 4 pi squared c squared, and you go back. Then this is equal to 4 pi squared c squared f, go back. Then, since this quantity is positive, you can, it's exactly like when you have matrices, when you have the eigenvalues of a matrix that are positive, right? You can define now any function that is defined in the positive. For example, you can define the square root here. Right? Or you can define this to the alpha, half, alpha, half. Then this is alpha, half, alpha, half. Then you can say that this is to taking, this is derivatives of order 2, this is derivatives of order alpha, in that order. Then we can define derivatives of order alpha of f like minus Laplacian to the alpha half of f, that is equal to 4 pi squared c squared alpha half f and backward. Okay? This is like the derivatives, homogeneous derivatives of order alpha. Okay? You can define anything you wish, that any function that have domain here in the positive. Okay. This is one thing. Second thing, who is the Fourier transform of this quantity? Well, that's not so clear because this is not an L1 function. It may be, you can decompose these two things. Suppose that for appropriate value of alpha, this function is okay around 0. It's in L1. And around an infinity may be okay in L2 if alpha is not very big. Okay, suppose that this makes sense. Who should be the Fourier transform of this? we are talking about this is a distribution, right? I mean, it's a function. I mean, okay, this is a homogeneous function. This function is homogeneous. Okay, let's recall, suppose that f is homogeneous of degree k if f of lambda x is equal to lambda k f of x. Then this function is homogeneous of degree minus n plus alpha. Is that okay? Okay. What happened, roughly speaking, if you take a Fourier transform of a function that is homogeneous of order k? What do you get? Suppose that you have f, and you want to take Fourier transform. Then, who is lambda c is going to be right? I put lambda c here. Now I switch variable. I have this is e to the minus 2 pi I. Then I call lambda x equal to y. Therefore, this is yc. Okay. Okay, what is exactly I'm trying to say? I want to say what is the Fourier transform, what is the homogeneity of the Fourier transform of this one is this. Okay, this is what I'm trying to do. I have this. This is f of y over lambda dy over lambda to the n. Is this okay? Okay, now this function is homogeneous of degree k. Therefore, this is 1 over lambda n plus k e to the minus 2 pi I yc f of y dy. This is f okay. Then we have, if this is homogeneous of degree k, imply that the Fourier transform of C is homogeneous of degree. What is the degree? Minus n plus k. Does that make sense? You have to help me to be sure that I get the right number. Okay? Okay. Therefore, what do you have here? This function is homogeneous of degree what? This is homogeneous of degree alpha minus n, right? Therefore, this one, it will be homogeneous of degree what? N minus alpha. Okay. Therefore, this one is homogeneous of degree minus n plus. No, I have something wrong, because at the end have to disappear. Minus. Okay. Okay, you are homogeneous of degree minus alpha. Is that okay? This is, on the other hand, if this function is radial, the Fourier transform is radial. Whenever you have a radial function, the Fourier transform is radial. Then the Fourier transform of this one doesn't have any other choice as a distribution to be this one. Because if you have to be radial and you have to be homogeneous, you have to be that one. Okay? Is that okay? Therefore, we have this part. And now, what is exactly that you are doing here? Let's rephrase this part. You are saying that I sub alpha of f is exactly equal to 1 over x n minus alpha convolution with f. And you are proving that I sub alpha of q is less or equal to some constant f in p, when q is better than p by this factor. Okay, you take Fourier transform here and write everything back. The Fourier transform of the first, this is the Fourier transform of the first, multiply by the Fourier transform of the second and go back. Right? You're taking convolution. Then this one is what we have before. This one will be this. Then if you want to write that, this is equivalent, completely equivalent to write this. Except for a constant that we forgot. Okay. Is that okay? Suppose that I take 1 over alpha f Suppose I take G I want this to be the f equal to d alpha of G. Suppose I take now this. What is exactly that you are taking? You are taking, if you take Fourier transform, you are saying this is equal, the Fourier transform of this, except for a constant, let's forget the constant, is c to the alpha g. I take Fourier transform in both sides, I get, from that formula, I get this. Is this okay? Therefore, this formula is equivalent to write, if I write this here, I get just f. I write f here, this part disappears, I have the Fourier transform of g, the Fourier inverse, this is g, q, and I have here the derivatives of order alpha. Oh. And this is what you are really proving. If you have a function that the derivatives is in LP, this function is better than LP is in LQ with this relation. And that is the best possible because homogeneity doesn't allow you any other value. Okay? Therefore, that's the reason why you have, this is called the fractional integration, but you put Sobolet here because what you are proving is this. Okay? Okay. Then to prove this in a serious way, you have to use this. Okay? What do you mean in a serious way? Well, it's not clear from the beginning that this integral makes sense. What you're going to do is how the proof goes. You split this kernel in two pieces, close to 0 and close to infinity. And you put an epsilon there. Close to 0, this is in L1. Close to infinity is in LQ. Then you do estimate in both and so forth. Right? But, okay, let's try to do it. Okay, it's clear that this is equivalent to this. And let's try to prove that. And then we still have time to the last thing that we want. Okay, let's try to prove this. Proof of this. Proof of one. Okay. I alpha of f is just the convolution. All the constant will be 1. X n minus alpha convolution with f that is equal to the characteristic of the ball of center 0 and radius epsilon this plus the characteristic of the ball complement 1 over x in alpha. Okay, this is equal to 1 plus 2 of, let's put A1, A2. This is A1. This is A2. Okay, how big is A1? How big is A1? A1 is the convolution of this function with this one. This function is in L1. This function is in LP. Therefore, I can compute the LP node there. Therefore, this is less. When you take F convolution with G in LP, is less than F in L1, G in LP. Why? Why this is true? Because this is true by Fubini. If you take everything in L1, you have this. And if you take things in L infinity, this is the supremum in X. Then you take the supremum in psi, you take this in L infinity, and you stay with the integral of f. Therefore, this is less than this. Therefore, if the convolution send L1 into L1 and L infinity, then you have to send LP into LP by the previous theorem, right? And the bound that you have is exactly the same. You take, this is a L1 node of this. Therefore, this is less than the LP node of L1 node of this. LP node of that. Okay, what is the L1 node of this? This is the integral between 0 and epsilon. You are in n dimension, n minus 1. I already passed to radial coordinates. This is r n minus alpha dr, and therefore this is exactly equal to integral between 0 and epsilon, the n di alpha minus 1 dr. This is epsilon to the power alpha, right? Divided by something. Okay, all the constants, irrelevant constant, okay? Okay, this is epsilon to the alpha. Is this okay? Okay, let's go here. Then, one second, I don't want to misstop since. No, I'm sorry. I'm not doing this. I apologize for the moment. I return here. Okay. I'm bound this pointwise. Then I cannot go with the NOR. Okay? I cannot go with the NOR. I'm doing this ahead of time. Who is this part here? Okay. The L1 NOR that I just compute, the L1 NOR of this was epsilon to the alpha. Then I go epsilon to the alpha, 1 epsilon to the alpha, the characteristic of the ball of this 1x n minus alpha, this f. Okay, this is exactly what do we have here. This is the convolution with this kernel. How is this kernel? This kernel is the characteristic of some ball and is decreasing, is 0 after that, is integrable. Then this is controlled by the maximal function. Okay? Therefore, this is less. The measure of this in L1 is exactly this quantity. Okay? Then what I'm using is the following. If phi is positive, radial, non-increasing, then the supremum in T positive of phi of x minus yt 1 over t to the n convolution with f of y dy is bounded by the NOR in this in L1 by the maximal function of f. Okay? Why? Because the maximal if you do this for simple functions, you will see that you are doing linear combination of maximal function. Then what we have here is the maximal function. What happened with 2? Okay, with A2 is a computation that we did last time. Is if you have, we want to compute the L infinity NOR of this, because we want to bound that. If you take F in LP and G in LP prime, 1 over P plus 1 over P prime equal to 1, the convolution of these two is in L infinity. And you have this. Why? Now let's do it here. You have y, and you want to compute the supremum of that. Right? You have. Is this okay? Okay, take now Holder estimate, and that's it. Okay? Holder estimate will do it. You take the LP of this, the LQ of this, the translation doesn't change anything, you have that. Okay, therefore we have to compute the LP of this and the LP of this and the LQ of this. Okay. This is less for all x that the LP of this and the LP prime of this one. Okay. You have to believe that after some computation, this is going to give you epsilon n over p prime minus n plus alpha. It's a computation. I mean, that's not a big deal. Okay? Now you have that this piece is bounded by the maximal function at x plus f in LP epsilon to this power. Okay? Then what do? You minimize this in epsilon. What is the minimum of this expression in epsilon? When this quantity and these quantities are equal. Minimize in epsilon. Okay? When you minimize in epsilon, you will finish that this quantity is going to be equal to f in LP to the power theta, the maximal function of x to the power that depends of x, to the power 1 minus theta, and theta one minus theta by q is equal to p. Now you have this. You minimize this, you get rid of the epsilon, and these two expressions will be exactly the same. That is going to be this one. You have a constant here. And now you integrate this in LP. Therefore, you want to finish with this in LQ. And sorry, you have I sub alpha of f in LQ is less than or equal to this is a constant for you. The maximal function of f at 1 minus theta in LP. Sorry, Q here. Because I'm taking the LQ norm. This is a constant, LQ norm. This quantity gives you exactly the maximal function of f in the norm P, because this power with this one gives you P. But you have the continuity of the maximal function that gives you this. Okay. And sorry, let me stop here because I was thinking in this way that I have to estimate. Okay. Then you have used the maximal function that controls this piece. And this piece is okay because this is in LP prime and this is in LP. You bound this and you have this estimate. Okay. We will use this estimate. Plenty of time. We have one more estimate that I will state, but I will not prove. And we will start on Monday with this one. This is the following one. Suppose that you have the maximal function. Suppose that W is positive. W is locally integrable in Rn, and you want this, the maximal function of f to the power p W of x dx less or equal to some constant, the function in p with this measure. That implies that W satisfies. Okay, we want, what you are trying to say is, I don't want now, I know that the maximal function is continuous from LP into LP when I put the Lebesgue measure. I'm not putting this measure. What you are saying is the maximal function of f in LP with this measure is bounded by f LP with this measure. What is the condition that this measure has to satisfy? Is that okay? It came out that the condition that you get here, it will be if and only if, and the condition that you get here is exactly the same condition if you put Hilbert transform here. Okay? But we will deduce the condition here. Okay? only that part. We will deduce that. I mean, it's a complicated since to prove that it's necessary and sufficient. And if you control the maximal, you control the Hilbert transform in one dimension. If you are in more dimension, you control the singular integral operator. But that's more than we need. Okay, we're going to see what is the condition that P need to W have to satisfy. And once we have this on Monday, we will be able to prove the Hardy uncertainty principle in L2 without using any analyticity. No analyticity, but this is a formal argument. And then we go back and say, how can we prove this formal argument? And then we go to estimate with weight in Schrodinger operator. Okay, we can stop here.